All right, good afternoon, everybody. Excuse me. Com check, com check. Elijah, can you hear me? Okay, good, good, good. All right, so I'm teaching from my office today, which is always interesting to see how many disruptions we have. And I don't know what they're doing outside, but it sounds like they're crushing asphalt or crushing concrete or something. And hopefully the filters on my microphone are good enough that you guys won't pick it up. But um, it's kind of distracting to me. But anyways, we'll give it a whirl. Today is class session 14, Thursday, October 5th. Okay, I don't have any office hours posted tomorrow, but if you need me, go ahead and reach out. That goes for the weekend as well. I haven't put together my schedule for next week yet. Monday is going to be kind of an odd day. It's a reading day for us. Doesn't directly impact this class since we don't meet on Mondays, but we have a symposium going on where we're bringing in some panelists from outside of Cincinnati to engage in a discussion about curriculum and structural engineering. So the bottom line there is that I won't be available very much on Monday to answer questions or to meet with anybody. I'll have to look at my schedule. I'll post my schedule on Canvas so you guys know when I'm going to be available. I'm thinking that I'll probably have office hours on Tuesday again, but I don't know yet. I haven't got that far. I'm a little behind in my stuff this week. So if we look at the submittals that we have due, you guys have a homework due tomorrow at 5 o'clock on beam modeling. I hope you haven't waited till the last minute. Putting together the models probably won't take a whole lot of time. It might take a little bit of trial and error, but sorting through the output will probably take a little bit of time for you guys. So excuse me. Frankly, I'm so far behind in grading now that if that didn't come in until Monday, that wouldn't kill me anyways. But I posted homework number 5 and homework number 6 when I was on Tuesday evening after class. And I had forgotten that I had a homework assignment dealing with truss elements and local coordinates. And so when I went to post homework number 6, or the matrix analysis of beam assignments, I was reminded that there was another matrix assignment that I wanted to have in between there. So the homework number 5 just asked you to rework homework number 2, but using local coordinates for the truss elements, and then use pre and post multiplication with the transformation matrix. So hopefully that won't be too challenging for you. I expect that it will be maybe an hour's assignment for each of you, maybe a little bit less for some, maybe a little bit more for some of you. There's 70 points associated with it. I just decided to award 10 points for each of the 7 matrices. So that's what constitutes homework number 5. Homework number 6 is matrix analysis of beams, and that one is a little bit more involved. We ask you to do an Excel analysis or a matrix analysis of the beams that you've been modeling in homework. I guess homework number 2 and 4, and so that one's a little bit more challenging. There's no moving loads or anything like that in it, but it will take you a little bit of time to calculate the equivalent end actions. And there's actually a bit of a difference in the requirements for undergraduates and graduate students there. So anybody registered for 5188, you're permitted to handle the snow load in a different way than folks that are registered for 6088. And if you're registered for 6088, I want to see a full set of calculations for the triangular loading at the right end of the beam. And if you're in 5188, then you can just use the equivalent end actions that I've given in the assignment. That one aspect, that triangular loading, for whatever reason, when I went and solved the assignment, that took me probably an extra hour just by itself to get those equivalent end actions. So I'll take it easy on the students who are registered for the undergraduate version of the class. Right. So I've just arbitrarily selected Friday the 13th for the truss assignment, and it should be Wednesday the 18th. Sorry, that's a typo, for the beam assignment. And so we'll go with that. The next homework assignment is going to be something to do with SAP 2000 again. So kind of going back and forth with these assignments. Anybody have any questions about homework or anything like that? All right. Yeah, so with that assignment due tomorrow night, yeah, I'll work on grading over the weekend, but I can't imagine I'll get through homework number 4 over the weekend. I'll probably my hope is I have to grade something for my steel design class, and then grade homeworks 2 and 3 for this class, and that would be a good weekend for me. All right. Let's shift gears a little bit. I didn't post this before class, but I wanted to work through an example problem. And the reason I didn't post it before class is I wasn't done until about 10 minutes ago with this example. So I'm calling this beam example number 2, but I might renumber them because it's a little bit out of order. This is, beam example number 1 was the simple cantilever beam with a point load. Beam example number 3 was a 2-span beam, and then it had hinges in it. And we never talked about beam example number 2. And this one's a little bit more complicated than the other ones. And so I don't know if it should be number 2 or number 8 or whatever. But anyways, what we have is a simply supported beam with a span length of 26 feet that's subjected to dead load and live load. And the dead load is 1.2 kips per linear foot, and the live load is a center point load of 16 kips. And so what I want to do is an analysis of this beam. And the reason I'm showing it to you now is twofold. One, it has 2 different load sources, as dead load and live load. And that's a reflection of homework number 6, where you have 3 different loads. You have dead load, live load, and snow load. And so I kind of want to illustrate how to handle different load cases or different load patterns in one analysis. And then the second reason is we're going to use this beam as a conversation piece for our next discussion on property modifiers. So anyways, when I go through and look at this beam, the first thing I'm going to do is decide on how I'm going to model it. And what I'm going to do is break this up into 2 elements, and I'm going to put a node at the left support. I'm going to put a node at the right support, and I'm going to put a node at the center of the beam underneath that 16 kip load. This certainly is not the only way that we could model this beam. I could model it using only 2 nodes if I wanted to. But I thought that this made sense. And so one of the first steps that we have is to develop our stiffness matrix. Even though we have 2 different load cases or 2 different load patterns for this particular beam, we still only have 1 stiffness matrix. The structure itself is the same for both load cases, so we have just 1 stiffness matrix. So here's the element stiffness matrix, K sub A, the element stiffness matrix, K sub B, and then when I assemble them, you get the global structure stiffness matrix as shown there at the bottom. And so my degrees of freedom are labeled up there at the top. So you can see that we have degrees of freedom 1, 3, and 5 are displacements. Degrees of freedom 2, 4, and 6 are rotations. All right, I think what I call out the beam is a W12 by 65. So that has a moment of inertia of 533 inches to the 4th. And then each element has a length of 13 feet. And this is one place where I tend to confuse myself a little bit, is you sometimes I'll check my work and I'll calculate the deflection PL cubed over 48 EI. And when you use the L value in that PL cubed over 48 EI equation, it's the span length of the beam, not the length of the elements. And so you have to be careful when I'm doing these types of problems to the point where I actually have a scratch pad where I write the stuff down, because it's easy to get confused, especially when the element length is half of the span length and blah blah blah. Anyways, there's my unrestrained global structure stiffness matrix K. All right, the next step is to look at the loads, and I'm going to examine the loads for the dead load case first, a uniformly distributed load with a magnitude of 1.2 kips per foot. And the first thing I'm going to do is convert that load from kips per foot to kips per inch, because we're going to work in kip and inch units. And that's another obvious mistake that we can make. So 1.2 kips per foot is equal to 0.1 kips per inch. And then when we calculate the equivalent end actions, we need WL over 2 for the vertical forces at the each end of each element. And then we need WL squared over 12 for the magnitude of the moment at each end of each element. And so when we break that structure into its 2 elements, you can see the equivalent end actions that are shown there in green. Now, when we write the vectors that correspond to the equivalent end actions, I have a piece of E for member A or for element A. I have a piece of E for element B. I have to be cognizant of what we defined as our positive directions or positive rotations for the degrees of freedom. So the 7.8 kips is negative in each case because that is pointing in the opposite direction of degrees of freedom 1, 3, and 5. When we look at the moments, the first moment at the left end of member A is going to be negative because it's opposite of what is positive for degree of freedom 2. The two moments at the center, 202.8, when it acts at the right end of member A, it is a positive value, but when it acts at the left end of member B, it is a negative value. And both of those are compared to the positive sense of degree of freedom number 4. And then when we look at the moment at the right end of member B, that's a 202.8. That's positive because it's the same sense as a positive rotation for degree of freedom 6. So what we're going to do is take these two equivalent end action vectors. Each of them is a 4 by 1, 4 rows, 1 column when we write it in the context of the elements. But I'm going to assemble these into a common equivalent end action matrix. And so I'm going to go through that assembly process where I augment each of those vectors with other degrees of freedom. So they're each now 6 by 1, 6 rows, 1 for each degree of freedom in the structure. And then I can add them together. And you can see over here on the right where I have the total value of P sub E, that I basically just taken P sub EA and added P sub E for member B to that. And so it's interesting, we have 202.8 and negative 202.8 in the fourth entry for each of those two. But when we add them together, they offset each other and ultimately end up being equal to 0. And if we were to take all of these member actions that are acting right here in the center of this beam, then we would see that they cancel each other out, and we would end up with just a force equal to 15.6 kips. All right, I've drawn these equivalent end actions in green to remind me that they're not really acting on the structure, that those are just actions that are equivalent to the loads that are actually acting on the structure. And so if I draw them in green, then that's a visual cue for me that they are equivalent end actions as opposed to actual structure loads. And that's important because when we come back in the end and calculate member bending moments and member shear forces, we need to back those out and we need to remove those because they're just a means to an end. All right, so then the next step is to look at the live load that's acting on the structure. I have 16 kips acting at the center. And because I chose to put a node there at the center of the beam, then that 16 kip load is just a nodal load. And I call it P sub N to indicate that it's a nodal load as opposed to an equivalent end action. And so when we look at both sets of loads together, let's see, I have my dead load on the left. I'm representing it in terms of the equivalent end actions. I have my live load on the right. So what I'm going to do is I'm going to develop these load matrices that each have 6 rows and 2 columns. And this is where the difference comes in with the examples that we worked the other day. All the examples that we've worked so far have just a single column for the load matrices. And that's because we're just considering a single load case or a single load pattern. So my equivalent end actions, I have 1 column for the dead loads, another column for the live loads. My nodal loads, I have 1 column for the dead loads, another column for the live loads. And then the sum of those two also has 2 columns. And so you can see that for the dead load, that's represented entirely by equivalent end actions. And the live load is represented entirely by nodal loads. If we had a more sophisticated beam, you could have both equivalent end actions and nodal loads in both of those columns or in all 3 of the columns. Now for your beam, let's see, that homework, because it has a pin in it, you're going to have just a few nodal loads where the 22 kip or the 20 kip point load acts on that pin. Other than that, everything else is going to be an equivalent end action for you guys. So ultimately, we end up with this load matrix. I call it P total on the right. And so it's going to be 6 degrees of freedom, 6 rows, 2 load cases. So it has 2 columns. And so when we go and look at our solution process for this, I'm going to reorder and petition the stiffness matrices. I have my P sub F, the loads acting on the free degrees of freedom. I have a P sub R, the loads that are acting on the restrained degrees of freedom. And then I can invert and solve for the free displacements delta F. And so I have a center line displacement, a mid-span deflection, if you will, that is equal to 0.7982 inches for dead load and 0.6550 for live load. What I can do then is augment that, add in the displacements that I have for the restrained degrees of freedom. Those are zeros in this case. And then the next step would be to solve for my member end actions and then my structure reactions. Excuse me. I had a quesadilla for lunch, and that'd be better off just drinking water and eating a protein bar. Right. So for each of the two members, member A and member B, I have two sets of end actions. I have one set of end actions for the dead load, another set of end actions for the live load. And so in this case, if we look at the center line moment, the bending moment due to dead load is going to be equal to 1,420 kip inches. The center line bending moment for, oops, I'm sorry, I read the wrong number. The center line bending moment for dead load is going to be 1,217 kip inches, and the center line bending moment for the live load is going to be 1,248 kip inches. Okay, so when you go through and do your homework, I think I said it's either 4 or 5. I think it's 5 different nodes, so you're going to have 10 degrees of freedom. There's 3 load sources. There's dead load, live load, and snow load. So each of the load matrices are going to have 3 columns. All right, so it's a little bit more involved than these, but you can have these to work from as an example. Questions? All right, my intention is to post the spreadsheet that I'm using to do this work as on Canvas, so you can have a look at the source code. I wanted to wait until I finished this example before I posted it, so that's why I haven't posted it yet, but I'll do that in the next day or two now that I have this example worked out. All right, if there aren't any questions, then let's go ahead and shift our attention to the next topic, and that topic is property modifiers. All right, this kind of comes out of left field. A lot of you probably have some experience using these programs to do some modeling at some point or another. And so you probably have an idea of what member loads are and nodes and joints and things like that. But I'm willing to bet that most of you don't have any idea what a property modifier is exactly. So this is a really useful tool that's in SAP 2000 and to a lesser extent in visual analysis. And it's something that I find myself using more often than anyone would probably expect. So let's use this as an example of what a property modifier is. So here's the 2 beams that the one beam with the 2 loads that we were just looking at. And if we go back to our first principles, we could see, what the maximum bending moment is in each case, and we could calculate the maximum deflection at each case that's going to occur at the center line. And so we should end up with a bending moment of 1,216.8 kip inches for dead load. We should end up with a bending moment of 1,248 kip inches for live load. We should end up with deflections of 0.7982 and 0.6550 for dead load and live load, respectively. Now, we've already gone through and done an analysis of the beam. We could analyze it as a 2D frame. Here we have axial degrees of freedom. We haven't talked about that yet in our matrix stuff. We could analyze it as a beam like shown on the right, and that's what we did in our example just a few moments ago. So if I go in and model this in visual analysis like this, I get one set of results. In visual analysis, Then I can go and model the same beam in SAP 2000. Here I have both the load cases shown in SAP 2000. I've got dead load on the left and live load on the right. And if I compare the results from these analyses, then this is what I get. So the bending moments for dead load agree pretty well, 1,217 kip feet everywhere. The bending moments for live load agree pretty well, 1,248 kip feet everywhere. But when we look at the deflections, we get a different deflection out of SAP 2000 than we get out of our equation and out of visual analysis. And so you look at this guy here, that's an outlier, and that's an outlier. And the reason why those are different is because SAP 2000 is including shear deformations in the calculation of its stiffness matrix. I don't know if you remember this or not, or depending on who you had as your instructor for your analysis class, there are actually more than one source of deformations when you go and look at a beam subjected to transverse loads. When we calculate PL cubed over 48 EI as the centerline displacement for a simply supported beam subjected to a point load, or if we calculate 5WL to the fourth over 384 EI, those are all taking into account the normal stress that's in there and the strain energy associated with that normal stress. But there's a secondary source as well, and it's the strain energy associated with the shear stresses and the shear strains. And they aren't usually a primary player in the deflection or the stiffness of flexural members, but they can be. And how big a difference it makes is a function of the how the beam is loaded and what the beam looks like. If it's a rather short and stocky beam and shear tends to dominate the behavior of that beam, then shear deformations are going to be a larger part of the overall deformation of that structure. In this case, where we have a relatively long beam, 26 feet, and it's a relatively shallow section, it's a W12, shear deformations aren't a big player. In fact, it's probably going to contribute on the order of something about 3-4%, 5% of the deformation. So these differences in SAP 2000 are caused by shear deformations. Okay, so here's a discussion of what shear deformations are. Is assumed to be due only to normal stress causing shortening of the fibers. Plane sections remain plane. Deformations of the beam due to shear stresses are neglected. If you go to Timoshenko beam theory, the deformation is formulated based on both shortening elongation of the fiber due to normal stresses and racking due to shear stresses. Plane sections remain plane, but not necessarily normal to the longitudinal axis of the member. Now, which is right and which is wrong? Well, you know, and both of these are just different ways of modeling the behavior of the beam. I think Timoshenko beam theory gives us results that are probably more accurate, but you know, we're only aiming to be within, 5% anyways. So the takeaway, though, is shear deformations do affect the stiffness of our structures. And it can be important sometimes if we underestimate the stiffness of those structures. So it's probably better to include shear deformations if we can and if it's convenient. Elements are less stiff or more flexible. For statically determinate structures, the deflections will be affected, but the axial forces and shear forces shouldn't change, right? If you go back and look at our results from this analysis, the bending moments are the same, even in SAP, because this is a statically determinate structure. If we go and model a second beam that's indeterminate, then we might end up with different shear forces and bending moments out of our SAP model because it will be an indeterminate structure. All right, shear deformations are more important when the ratio shear stress to normal stress is higher. Shorter beams, higher shear to moment ratio. Deeper beams, higher shear stress to normal stress ratio. AISC has language in its specification that says that the effects of all of the following on the stability of the structure and its elements shall be considered: flexural, shear, and axial member deformations. So AISC in that statement says that we have to include shear deformations in our model. Yeah. Are you going to be are you going to be found to be in non-compliance if your model doesn't include shear deformations? Possibly, but it probably won't make that big of a difference if you're designing a typical structure, a 6-story building, a 10-story building. It probably won't make that much difference. If you're designing, a 50-story building, then now we're talking about the situation where shear deformations should probably be accounted for. What about the other material? ACI says that the moment of inertia in the cross-sectional area of members shall be calculated in accordance with tables, whatever, unless a more rigorous analysis is assumed. And if you go and look at that table, it says that the moment of inertia that you should use is 70% of the gross moment of inertia. And that's to account for cracking in the member, right? You deal with concrete, you put a member into flexure, the tension side of that member cracks, and you end up with a moment of inertia for that member that is lower than what you would get if you just took the base times the height cubed over 12. And so you have these modifiers that are used here in the ACI specification, 0.70, 0.35, 0.25, to account for a physical phenomena in the concrete that is modeled just using these modifiers. Okay, the magnitude of the shear deformations that we calculate, it depends on something called the shear area. And so the shear area is a function of which type of member we're using. And so these images, I think, come out of the user's manual for SAP 2000. If you have a rectangular cross section like you would have for a concrete beam, then the shear area, we usually call it A sub V to give it a notation. A for area, V is indicative of shear. It's 5 times 5/6 times the base times the depth. If we're looking at a wide flange section, then you can take 5/3 times the thickness of the flange times the breadth of the flange. And that's in the case where you have weak axis shear. If you have strong axis shear, then you just take the area of the web instead. And so this is a little bit strange. Notice how the loading is applied here, right? So in that case, you have a different shear area when the load is parallel to the web than you do when the load is parallel to the flanges. And so the shear area of the member depends on how it's loaded and what the shape of the member looks like. So by default, visual analysis does not include shear deformations, but it can if you want it to. By default, SAP 2000 does include shear deformations, but you can tell it to neglect them if you want to. And so both of the programs are rather dynamic. They can include or can exclude, but they make a different choice to how to handle them by default. And so when you go and compare results that you get out of SAP 2000 with results that you get out of visual analysis, it's not uncommon to see differences in the two sets of output because of the way that they handle shear deformations. If you go into visual analysis and you look up the results of a member, so here's our W12 by 65, then you can see a lot of properties here. You have the area A equal to 19.1 inches squared. You have the moment of inertias, 533 and 174. You have the section moduli, the polar moment of inertia, the warping constant. All the way down here at the bottom are two values called SA1 and SA2, and those are the shear areas for this particular member. The shear area 1 is for a load that's applied vertically, and shear area 2 is for a load that's applied horizontally, I think. I don't use it often enough to know that for sure. And so when those values are set to 0, then that's an internal switch for visual analysis that says, hey, let's ignore shear deformations entirely. So there's an if statement someplace during the assembly process where if the shear area is equal to 0, we're just going to ignore the shear area entirely. And so by default, let's see, well, that's a typo. SA1 and SA2 are set equal to 0. Let me circle that so I can fix that for the next time, which tells SAP to exclude shear deformations. Shear effects are included only for user-defined sections with non-zero shear areas. And if you want to include shear deformations in your visual analysis model, what you have to do is go in and define a user-defined cross-section and then enter manually the values for SA1 and SA2. That's kind of tedious. It would be nice to have a little checkbox to be able to include or exclude, but for whatever reason, the programmers for visual analysis chose not to do that. All right. To include shear deformations, elements must be defined as custom blobs or user-defined cross-sections. Now, if we go in and look at SAP 2000 in contrast, here's our section definitions for the W12 by 65. There's a button down here at the bottom that says show section properties. And if we go in and look at the section properties for that, what you can see is that we have the same area, 19.1. We have the strong axis moment of inertia, 533 inches to the fourth, the weak axis moment of inertia, 174, et cetera, et cetera. And then, where is it? Here it is. The shear area in the two direction is 4.719 inches, and the shear area in the one direction is 12.1 inches. So if you take the thickness of the web of that W12 by 65 multiplied by its depth, you would get 12.1 inches squared. So if you go in and try and change those numbers, you can't do it, though. It won't let you change them because it's a database shape, and if it lets you change them, then that would create all kinds of problems. But there is a way to change that indirectly. So to suppress shear deformations in SAP 2000, we're going to use these things that are called property modifiers. Property modifiers are basically scale factors that you use to modify computed section properties in SAP 2000. They can be used to suppress shear deformations, our current conversation. They can be used to account for cracking of concrete or for other factors that are not easily defined in the geometry or the material property tables. For example, in steel design, we talk about something called the stiffness reduction factor when we have inelastic buckling of columns. You could use a property modifier to account for the stiffness reduction of our structure when inelastic buckling governs the strength of a member. Right, so here are some applications. Model cracking, model reduced stiffness due to residual stresses and partial yielding. That's stiffness reduction, same thing. Indirectly, including other structural effects in the model. And so individual modifiers are available for the following 8 terms. I only count 1, 2, 3, 4, 5, 6, 7. But there are shear stiffnesses in 2 directions. There are bending stiffnesses as well. So here are the property modifiers. And so let me go back. There's, if we go back to this, no, not that, that's the same slide, dummy. If we go back here, there is a button at the bottom that lets us set the property modifiers for that cross section. And so if we click on that button, then that brings up this dialog box here, and we can go in and set these modifiers to some other value. By default, they're equal to 1, which means we just take 1 times whatever value. So we take 1 times the cross-sectional area that was defined for the W12 by 65. We take 1 times the moment of inertia that was defined for the W12 by 65, but we can set these to other values. In fact, if we want to suppress shear deformations in our SAP model, what I typically do is I come in and specify a value that is sufficiently large so as to render the shear area as infinity. And I usually type in 6 nines in order to get there. And that takes me to 7 orders of magnitude larger than what it would have been otherwise. And if we go and modify the model that we had at the beginning of this lecture using these 2 property modifiers, then what we get are deflections out of SAP 2000 that are almost identical to the deflections that we got out of our theoretical solution and out of visual analysis. Okay, so how do these work? Well, if we go in and look at our stiffness matrix, here's the stiffness matrix for a beam element. What it's doing is it's basically applying a modifier to the section properties that we're using in the formulation of that stiffness. So if I were to put a property modifier on this element stiffness matrix for the moment of inertia, it would take the property modifier times whatever value of I is stipulated here, and it would use that in the calculation of the stiffness. Now, we could also look at it in the context of a frame element. We haven't talked about frame modeling yet in matrices, but this is the element stiffness matrix for a frame element in local coordinates, and you see that we have an axial term AE over L that's added in there as well. And so in that case, it would be modifying the value of A for that particular stiffness coefficient, and then we could modify the values of I here. So one thing that's left out though is the material properties E. And as it turns out, in SAP 2000, you can modify the material properties as well. Now, you have to be careful. There are several different places in SAP 2000 where we can modify the section properties. Several places where we can stipulate property modifiers. We can apply them to a cross section that we're using in our model. You could apply them to the W12 by 65 cross section, or you can apply them to individual objects like a frame object or a beam object. So it's possible to apply these modifiers twice, and that can be problematic. If you go in and specify a property modifier of 0.7 for a cross section, and then you go and click on a frame element and specify a modifier for that frame element of 0.7, then what it's going to do, it's going to multiply 0.7 for the first case times 0.7 for the second case, and then multiply that times the stiffness quantity that you're modifying. So you do have to be careful there. And as I understand it, you can also apply modifiers to materials as well. So you can modify the mass, you can modify the moment of inertia, you can modify, not moment of inertia, modulus of elasticity. You could also modify shear modulus of elasticity, et cetera, et cetera. Modifiers cannot be assigned directly to a non-prismatic section property, but any modifier, okay. So these are useful, especially if you're modeling concrete. I have an assignment where we go in and do modeling of concrete. It's like my one token assignment to include to be non-denominational in my course. So we might explore that. So it's useful, and we can do it. You can use property modifiers in other cases as well. Another case where we do it is if we have a two-dimensional model of a building, and I want to include the rigid diaphragms. You know, when we have a floor slab that is rigid in plane, you can specify a property modifier of 1 million for the cross-sectional area of a member, and that is a good way of modeling rigid diaphragms in a two-dimensional model of a structure. So they're very useful, but they're also very powerful, and they require a modicum of understanding by the user of what they're actually doing. And so when you guys are bemoaning my lectures on matrix analysis, you know, they get kind of mathy. They get a little bit involved. It can be tedious when you're trying to chase an error or find a mistake in the matrix stuff. The reason why I insist on including that, one of the reasons why, is for things like this. If I tried to explain what a property modifier is without you guys understanding what a stiffness matrix was, then I don't think that this would be as impactful as it is. All right, so what about visual analysis? Well, visual analysis includes something similar to a property modifier. They call it a stiffness factor instead. And so if you click on a member, then you can go in and modify these stiffness factors. They have stiffness factors for I sub y and I sub z. So that's the strong axis and the weak axis moment of inertia. They include a modifier for the area as well. And so these modifiers are a little bit different. It's what percent of those values that you want to use. So if you want the full value, you type in 100 here, and that means you're using 100% of the value that was stipulated for that cross section. So if we were modeling concrete and it was a flexural member, we would use 70% of the moment of inertia. And if we were doing the same thing in SAP 2000, we would stipulate a property modifier of 0.7 instead. All right, so that's the end of that conversation. an interesting discussion. I'm surprised nobody's asked me about it yet. Maybe you've noticed that some of the results that you get out of SAP 2000 are a little bit different than what you get out of visual analysis, but maybe you've just been dealing with so many numbers that you haven't really had a chance to digest the results. And so that's probably the reason why. When somebody asks me that question, usually the answer is because SAP 2000 includes shear deformations and visual analysis does not, and we use property modifiers to make that change, make that accommodation. Excuse me. All right. Questions? All right. Who's missing? I know Edson is missing. There's somebody else missing as well. 1, 2, 3, 4, 5, 6. No, I guess that's it. Edson approached me yesterday after class and said that he's been watching the recordings, and so that's why he's not here. He's not the only one. If you look at the logs in YouTube, the videos for this class tend to get a lot of views, which is odd. So if I went back and looked at the analytics associated with lecture 11 or 12 from last week, they're probably 50 or 60 views, which is crazy because I don't think my fan club has that many members in it. So I don't know what's going on. Maybe I know what it is. I bet you parents around the world, are putting on my lectures in the rooms of their children so that they can put their kids to sleep. That's probably what it is. They're using these lectures for their babies so that they can get them to go to sleep. Instead of playing like lullabies and things like that, they're going to play matrix analysis and structural analysis by Jim Swanson. All right. So here's lecture number M8, I think it is. Maybe it's M7. And this one is on automatic meshing and element deflections. And so what we're going to do here is start off with a review of what output stations are. I think you guys, in working through your solution for tomorrow's homework, probably have an understanding of what output stations are by now. They're basically designated locations on a frame element where output forces are calculated, where design checks are calculated, and they're used for plotting points on graphical displays of force diagrams. Excuse me. When output is exported to tables, it's only exported at these pre-designated places. So we use this as our sign convention. Well, at least I do. Moments positive on the top fiber. Shear is positive if it's right if it's acting downward on the right-hand end of a left-hand section, acting upwards on the left-hand end of a right-hand section. And then here's our beam element formulation. When we've talked about this ad nauseum, and this point right here, the point where we're calculating a moment or a shear, this would be an output station for our member. Now, it's most accurate and practical to use a sufficient number of output stations, but not an excessive number. I usually use 9 intermediate points, so it gives me output at the 10th points of the members. So SAP will automatically report the output of each element unless there's a rigid offset defined. In that case, you get something a little bit different. We haven't talked about rigid offsets yet. Defining 11 stations results in output at 10th points. And so this is how we define that. All right, so users who want to obtain exact numerical values for the response at points other than output stations may use diagrams for frame objects. So let's go back and look at our beam again. We have a 26-foot long span. We have a dead load of 1.2 kips per foot, but in this case, I'm going to change up the loading a little bit. Instead of having one single point load at the middle, I'm going to have 2-point loads spaced 8 feet from each end of the member. So our bending moment diagram remains unchanged from the last lecture with respect to dead load, but it changes with respect to live load. So now we have a moment at the center of 1,536 kip inches. We have a centerline deflection of 1.0565 inches. So what I'm going to do is I'm going to go in and I'm going to play with the number of output stations that we use for our beam. I'm in SAP 2000. I've generated a model of this thing. I've got 2 nodes, one at each end of the beam in this case. So I should stipulate that, I guess. There's one node here and then there's another node there. So I've got one member and two nodes, or one element and two nodes. And so if I specify two output stations, that's basically going to give me output only at the ends of the member. And so if I go in and look at my results, look at the values that I get here. When I look at the bending moment, I get a moment, let's see. See, the shear force is 15.6 kips. That's okay. The beam displacement that I get, deflection in the two direction, that's equal to 0. And the bending moment that I get is equal to 0 as well. So I'm basically getting garbage output for these results. And so you might wonder why. Well, the answer why is because I'm only calculating the values at the end of the member, right? Two output stations gives us output there. I should come in and fix these. I don't think these are right. I should come back and look at those. For the shear force diagram, it works out just fine for the dead load case. For the live load case, it's not right at all, right? The bending moment diagram for live load should come up like this and then go back to 0, then come right. And for the bending moment diagram, it should be like that, but it's not giving me the right output at all. If I go in and specify 3 output stations, now I have output station at the left end, the right end, and at the center line. Now things get a little bit better. My shear force diagram looks better over here. My bending moment diagram is not quite right. That should be parabolic, and it's not. This bending moment diagram isn't right either. But now I have beam deflections, right? I've got a deflection of 0.806 for live load, a deflection 0.6386 for dead load. Let's see. If I go in and specify 4 output stations, now things are getting a little bit better. This shear diagram is still good. This one is closer, but still wrong. This one doesn't look terrible. This one is supposed to be parabolic. And as you can guess, by the time we include more and more output stations, we end up with results that are closer to the value that we need. But even if I go in and include 11 output stations, I calculate the results at the 10th points. My bending moment is pretty good. I've got a 0% error there. Bending moment here is pretty good, 0% error. But look at the deflections that I get. If I calculate the deflection there, I end up with a small error, 0.7518 versus 7982. And if I go over here and look at this deflection, I get 1.0528 versus 1.0566. So that's not too bad, but this one is off by a fair amount. Now that difference isn't shear deflection. I'm using a property modifier for shear of 6 nines, almost a million. And so I can't attribute that error in the beam deflections to the shear deformations. Now, why is that there? Well, the reason why is that in between nodes, SAP 2000 doesn't use exact structural mechanics to calculate beam deflections. It actually uses a cubic interpolation to calculate the beam deflection in between nodes or joints. Now, I'm going to have to be careful here because I'm using the words nodes and joints. They mean the same thing, but I've also been talking about output stations, and output stations are different from nodes. So we have, in this set of results here, we have 11 output stations defined, but we only have 2 nodes defined for this particular element. So we have output stations defined all along the length of this guy, but when we go in and look at the nodes that we have defined, we have a node only defined here and here at this end. So what it has to do is it has to use a cubic interpolation to estimate what the deflected shape of the beam is in between those nodes. So why is it using a cubic interpolation? Well, because the general form of a cubic equation looks like that: ax cubed plus bx squared plus cx plus d. And so with that cubic interpolation, that allows us to use 4 coefficients or 4 constants, a, b, c, and d, to characterize that equation. So if we go in and look at our beam element formulation, we basically have 4 deformations along associated with that element. We have 2 deflections, a delta I and a delta j, and we have 2 rotations, a theta I and a theta j. So when we have only 4 different deformations associated with each element, the best we can do is a cubic. If we went and tried to use a 4th order curve, we would have ax to the 4th plus bx cubed plus cx squared plus dx plus e. That would be 5 constants that we would need, but we only have 4 boundary conditions. So we can't use a 4th order curve. So the way that this shakes out is like this. We can go in and say that the deformation q at x equals 0 is equal to 0. So q is our displacement. We can say that the deformation q at x equals L is equal to delta J. And then we could say that the derivative of q at x equals 0 is equal to theta sub I. And the derivative of q at x equals L is equal to theta sub J. So if you go through and write these 4 boundary conditions and apply them to the general form of our cubic equation, what you can solve for are those 4 constants, A, B, C, and D. And so I did that, and I did it by hand several times, and I decided not to type it up, and I just scanned these pages instead. And so here's the funny part. I got all the way through this and realized there was an error someplace, so I got try again there, right? And so ultimately what you can do is come up with equations that you can use to determine these constants A, B, C, and D. And if you go through and do it right, I think, then this is the values that we get for A, B, C, and D. So when SAP 2000 uses these beam diagrams, this red line that's down here at the bottom isn't an actual deformation of the beam. It's a cubic equation that's based on the deflections at the nodes at each end of the element and the rotations of the nodes at each end of the element. So then the question is, well, if that's just a cubic approximation, is that accurate or is it not accurate? Well, the answer is that it depends, right? And just like everything else, there's no black and white. So if we go back and look at our Euler-Bernoulli beam theory, we can see that the displacement Q of X is equal to the 4th derivative of the load. You guys probably remember this from your structural analysis. If you were integrating to find the deflected shape of a beam, you start with the load diagram, you integrate 4 times, and you get the displaced shape. So that means that we would end up with, depending on the type of loading, either a 3rd order curve or a 4th order curve. So if we end up with a beam that has point loads on it without any distributed loads, then the curve that we end up with after integrating, we go from a 0th order curve to a 1st order curve to a 2nd order curve to a 3rd order curve. So if we have a beam with just point loads, then a 3rd order curve does a pretty good job of approximating the deformed shape. But if you have a beam with a uniformly distributed load, then you end up with a 4th order curve, something times x to the 4th as the deformed shape of that beam. And so when you have a beam subjected to point loads, SAP 2000 does a pretty good job of estimating what the beam deflections are using that cubic approximation. But when you have a beam subjected to a uniform load, or even worse, a triangular shaped load, then SAP 2000 doesn't do a very good job at estimating beam deflections. It'll be close, but it won't be exact. And so if we go back and look at our beam diagrams back here, you can see that for the case on the right where we have a couple of point loads on the beam, it's really, really close, right? 0.01% error. But in the case on the left where we have a uniformly distributed load, we have an error that's 0.75%. That's probably not going to cause any real problems in any realistic structures, but it's not as close as it is for point loads. So when you go in and use these beam diagrams, I want you to be cognizant of the idea that these are approximations, and the approximations are good for beams loaded with point loads, and they're okay for beams that are loaded with uniformly distributed loads. Now, what happens if you want to get the exact results? Well, what you can do is you can go in and add a node at the point where you want to get exact deformations. If you want to know what the deflection at the midspan of a beam is, add a node there. And one way of doing that is going into SAP 2000 and clicking on that frame and say, I want to divide that frame into 2 frames. And so what it'll do is you can say, I want the frames to have the same length at each end. and then it'll put a node at the middle of the beam, and then you can go in and do a mouse over, and the deflections that we get shown on the left for dead load is exactly what we would expect based on our Bernoulli beam theory. So the takeaway here is that the only place that you get exact displacements out of a model are at the nodes. And so think about that with respect to our matrix analysis of beams. The only place where we're actually calculating values of delta are at the nodes within the model, right? Anywhere else we can calculate bending moments and shear forces, but we never actually calculate the deflections along the length of an element. And there's a good reason for that, because it's really, really hard to do. So that creates an issue. If we go in and look at our exact displacements, if we go back and put in, let's see, I'm leaving out something here. What I've got are two different elements. I've got an element here, element A, another element there, element B, the same thing here, element A and element B. So what I can do is I can right click on this member and then select beam diagrams, right? The diagram dialog. And then it shows me this, which is the bending moment diagram, shear force diagram, and display shape, but only for half of the beam, right? I took that full 26-foot long member, I divided it into two. So now this is a 13-foot long member. And look at the display shape. That display shape isn't at all what we expected it to be. And the reason for that is by default, the displacements in the diagram window are shown relative to the ends of the element. See this little checkbox down here at the bottom? So it's showing the display shape, but it's showing the display shape relative to the ends. If we want the relative to the absolute, we can click on absolute. And then here's the relative displacements. And then there's the absolute displacement. So if we go back and click on absolute instead, then we get a display shape that makes a whole lot more sense. So then the question is, well, do we always just want absolute? Why don't we just click absolute and make SAP give us absolute deformations? Well, the answer is no, you don't always want absolute deformations, because if we're looking at beam deflections in a structure like this, you don't want the absolute deflection of that beam, right? You want the relative displacement of that beam, not including the shortening of the column. So that's why they give you that option, right? So you have to be smart enough to know which one you want. So there is a better solution, and that solution is to use automatic meshing of the elements. And so what you can do is you can go into that model, right click on the 26-foot long beam element, and you can tell SAP, yes, this is one line object, but before you perform the analysis, I want you to subdivide it into X number of analytical elements. So you have one line object, you're going to divide it into, say, 10 analytical elements, and then you would have a stiffness matrix that has 10 times 2 would be 11, a 22 by 22 stiffness matrix for that one beam. And it'll do that. And then when you're done with the analysis, you can come back and right click on that single line object and plot the deflections and the moment diagram and the shear force diagram for all 10 of those beam elements that it used. I'm out of time, so I'll stop here. But when we get back together on Tuesday, I'll show you how to do that in SAP 2000. I've got still another 12 slides in here or whatever. But this is a very powerful feature in SAP 2000 that allows you to include a lot more nodes in your model. And that's a good thing, because the more nodes you have in the model, the more accuracy you have in computing deflections. But it's a bad thing, because the more nodes you have in your model, the bigger the stiffness matrix gets and the longer it takes to actually perform the analysis. Nowadays, that's not that big of a deal for us, but if you have a large model and you tell SAP to automatically subdivide every one of your line objects into 10 elements, then you could end up with a model that would normally take 30 seconds to run. It might end up taking 5 minutes instead. All right, I'll hang around for a few minutes if you have any follow-up questions. Otherwise, check on Sunday night or Monday morning for my office hours for next week, and then I'll either be available Tuesday morning for office hours or no later than Tuesday at 12:30 for our next scheduled class. All right. Thank you. Take care.